Vasudev Mittal from MS-90. He did his thesis in MIT. In fact, he's still currently working on it. And today he's here to present the first part of his thesis. So, over to you.
Thanks a lot, Fari, for inviting me. So, hi everyone, myself Vasudev Mittal. I am an MS-90 student from Mali, visiting researcher at the University of Sydney. Today I am going to present some of my recent results on the famous dipole and isotropy problem. And I am sure you all have read the abstract. So, I will not reiterate the importance that this problem holds for current generation of physicists. So, I have titled my talk as Testing Einstein and Ode to Anisotropy. Why I am testing Einstein here? Because Einstein was the first person to make the assumption that our universe was homogeneous and isotropic. With this, I am starting my talk. So first thing, this work is being done under the supervision of Professor Derek Lewis, who is our boss. He is Mr. Oliver Oida, a first-year PhD scholar at University of Sydney, and this is me. This is with a poster that we created based on our paper. And the thing is, we call ourselves as anisotroopers. So, with this introduction of the work, let me start. So, Einstein first stated that the universe is homogeneous and isotropic at the largest scale. This assumption gave us the famous FLRW metric. So, FLRW means there were four scientists: Friedman, Lemaitre, Robertson, and Walkman. All four of them contributed in some parts to deriving this metric. If you want to understand it, so I presume you guys have done some basic geometry, right? So in Euclidean space, your dr square is just dx square plus dy square plus dz square, correct? In special relativity, you say dx square is just c square dt square minus dr square. This is your Lorentz invariant line element. Now, if you go to spherical coordinates, you will have d, let me say this is dr tilde. Dr tilde square would be in spherical coordinates. Dr square plus r square d theta square plus r square sine square theta d phi square. And if you plug this thing here, you will see we almost have this structure that we are seeing here. The only two notable differences is the scale factor A and this 1 minus kr square factor A. So the scale factor of A is called the expansion factor or the scale factor, and it takes into account that your space itself is expanding as a function of time. In fact, since we only have a single parameter denoting our expansion rate, it means that we are assuming isotropy. And this 1 minus kr square factor, this comes from your geometry. So if k is equal to 0, then we are in a flat space-time and we get our normal structure here. If k is greater than 0, then we are sitting in a closed or spherical universe where you can find this factor, and for a closed universe, this k is actually 1. For an open or hyperbolic universe, this k would be minus 1, so you will get dr square by 1 plus r square. When we use this metric and apply some Einstein's equation, we get the equation of expansion for our scale factor A. These are the famous Friedman equations. Rho is the energy density for your constituents of the universe, and P is the corresponding pressure for different constituents of the universe. Now, in around 1998, two groups of researchers showed using supernovae that this A double dot factor was greater than 0, which means that the expansion of the universe was accelerating. The problem with this thing is that if you take matter or radiation, which are the two visible components of your universe, then you cannot explain why this A double dot is greater than 0. Hence they postulated that our universe is dominated by dark energy, which contributes around 70% to our universe total budget. So from this you can see that dark energy is actually a model dependent thing. And if this model breaks down, then ideally we cannot assume dark energy and dark matter for that purpose. But for dark matter, you will need a much deeper understanding. So for now, just understand that dark energy exists because we are assuming an isotropic universe.
What is A?
A is the state. It denotes your expansion rate of the universe. And if expansion is accelerating, A double dot is greater than 0.
Is it same as that Hubble constant which we talked about?
No. Hubble constant is your A dot by A at present time.
Okay.
A dot by A is your Hubble parameter.
Okay.
And at present times it's called the Hubble's constant.
So it can change?
Yeah, Hubble parameter changes with redshift.
Okay.
In cosmology, we don't use time, we use redshift. Because at the end of the day, you need observables. Now, the cosmological principle is supported by cosmic microwave background. So, do you all know about cosmic microwave background? Okay. So, cosmic microwave background is moved to 10 parts per million, a fact that supports the isotropy of the universe. But before reaching that level, we encounter a dominant dipole and isotropy of 1 part per thousand. So what we actually observe is a CMB like this, not the ones that is shown in the picture, all smoke black or anything. This is what is observed by Planck, W and other satellites. So when this was observed, what researchers said, okay, this is like a dipole kind of structure. So we will say that our universe is moving towards these galactic coordinates, that is here, with a velocity of 370 kilometers per second. That induces a Doppler shift in your temperature. Now, you might be wondering from where this formula comes from. So here is the thing. So photons are bosons. You all know that, right? And for bosons, our phase number density goes as e to the h mu by kb t minus 1. Special relativity tells us that this factor here is actually invariant of your frame of reference. It's a Lorentz invariant. Now, if you've done special relativity, then you will know that the frequency, modulated frequency actually scales as 1 minus beta cos beta divided by 1 minus beta square. This is how your frequency modulates due to Doppler boosting. And if this has to remain invariant, then your h mu by kbt should be a Lorentz invariant. It should not change under the frame, under the transformation of your frame of reference. It means that your mu by t should be a Lorentz invariant. So if you look at this structure here and this one, then you will see both of them are just opposite of each other. And if you do a ratio of mu by t, then this quantity will turn out to be Lorentz invariant. So using this kind of structure, beta is your v by c here. Using this kind of structure, we found that velocity was roughly 370 kilometers per second in the direction n hat, which is given by these coordinates, and n is your direction of observation. So n hat dot n is your angle theta. Okay. Now in 1984, Ellis and Bradley, they were two famous cosmologists. They stated that okay, if we are seeing a dipole-like structure, then all sky surveys of other cosmologically distant probes, such as your galaxies and your supernovae and your quasars for that purpose, should show a similar dipole, and they derived a formula for that dipole anisotropy. So what they assumed was that if in your all sky survey, the median redshift of your sources was roughly 1, if your flux depended on the observation frequency in a power law fashion, this second assumption is true regardless of your type of sources. It's a fundamental axiom. And if your number count density above some flux depends on that flux in a power law fashion, this was an assumption, and your number of sources is of the order of 100,000, then up to a leading order, your data would be modulated by this much amount. So if you initially have a number density n, so let's say there were n number of sources in a patch of sky, then due to this kind of modulation, it will become 1 plus d cos theta. Here theta is Theta is your angle between observed direction and the direction of your motion. D is your dipole angle. Okay, so initially what was an isotropic sky would be modulated to something like this. And you should contrast this with the structure that is shown here. So if the kinematic interpretation here is true, then both these dipoles that are observed in CMB as well as number constant, they should give you the same velocity. But the problem is they don't do that. And in 2021, a group of researchers using quasar data, the data set is shown here, they showed that there was a 4.9 sigma tension between the dipole inferred from CMB and the dipole inferred from quasars, which means you met a dipole. And if you know something about statistics, then you will know up to 3 sigma things are fine. 5 sigma, I will start to worry. But in 2023, some other people showed that it was 5.7 sigma. And above 5.5 sigma, it means that your theory is collapsing. So does it mean that standard model is gone? Standard model of cosmology is gone? If yes, then these equations are wrong. And it means that dark energy is gone. So millions of dollars spent to detect dark energy, do meaningful cosmology experiments, it's all history. Okay, we have a tension. So how to solve it? So if you know Chetan Krishnan, Rajni model and Shani Sheikh Jabari. Chetan and Rajni are from IASC and Shani Sheikh Jabari is from Iran. So what this said was that instead of an isotropic expansion, let's assume a dipole-like liquid. And they derived the equations of motion for a dipole-like liquid. This was one proposed solution. Second one involves perturbation theory and utilizes the so-called isotropism rules. Don't ask me about this because I'm learning about this stuff myself. So if you guys are interested, we can learn together. So now, we have a tension at 5.7 sigma and we should either resolve it or should state that this tension exists and we need to use this kind of structure instead of the isotropic structure. So here, in 2023 July, a group of researchers from MIT, Oxford and New York University, they gathered a new quasar data from Gaia. They created this quasar catalog and they actually gave 2 versions. The first version looked deep into the universe. The second version was a shallower version. For those of you who don't know, quasars are just a supermassive black holes that eject matter out to distant parts of the universe. So they created these 2 catalogs. When I started my master's thesis, I looked at it and said, hey, we have a new quasar catalog. Why not calculate the matter dipole in this one and see if the 5.7 sigma tension is just only this kind of data set, or is it also present here?
What does the G stand for?
G is your observation magnitude. So in cosmology, you have this apparent magnitude versus true magnitude kind of relation. So G is your apparent magnitude with which you observe. But quasars suffer from a problem. So you see, this is your galactic plane, grounded. In this region, we don't have any sources, and the number density of sources at the border is fluctuating. To mitigate this, the Quasar authors had considered 4 effects that are contributing to bad data values here. They first considered that around Milky Way, you have the problem of dust. So our galactic plane is actually dominated by dust. That is why we cannot look at our galactic center and anything. Then they said, since we are in the galactic plane, we will have lots of stars around it. So because of that, many sources here might be quasars. Then they said, okay, we have the 2 satellite galaxies, large and small Magellanic Cloud, which will have some extra stars. So they use this one. And finally they said that since this data was collected from Gaia, and Gaia is a space-based satellite, so ideally Gaia is scanning each point more than once, which means that there is a high probability that many sources here would be recounted. they combined these together and created the selection function rules. And they mentioned that if you are modulating your data set with these selection functions, then ideally you should get a catalog that is good for doing your cosmological analysis. So we modulated the rough data with this selection function, and then we did a sliding average, which gave us this kind of a catalog here. And we studied this catalog. So we have a data set. We want to calculate the method algorithm. We have a formula for the method algorithm. Here, question is, how do we do it? Enter Bayesian statistics. Now I have written Bayes theorem in this form because it will help in understanding what is going on. So assume that there is a model M with free parameters theta, and you want to fit it to a data set D. Then the probability distribution for your free parameters which you are fitting would be proportional to the product of likelihood of observing that data set given the model times the prior space, like prior constraints on your free parameters given your model. The proportionality is switched by modulation factor here, which is just the normalization of the numerator over parameter space and is dubbed as the evidence integral. Why is this called the evidence? Because this z factor here is used to calculate the base factor. And if you want to compare two hypotheses, let's say if you want to compare which model is a better fit, then you can always use this base factor. So a good exercise in Bayesian statistics would be to check, like in physics laboratories, you collect data points, right? And suppose that you are fitting a straight line. How do you know that a straight line is a good fit to your data and not some curve? So ideally what you should do is fit a straight line to your data, calculate its evidence, then fit some other quadratic or cubic polynomial to the data, calculate its evidence, and then you should subtract to see which one has better validity. So if your data is indeed has a straight line fit, then the base factor for a straight line would be higher than all other hypotheses of a second or third order polynomial. Okay, we need to calculate this posterior distribution here. But we have a likelihood function that we will construct artificially. We can define our prior function, but how do we do this integral efficiently? So in 2006, this guy Skilling proposed nested sampling, and he implemented this in the Python package Dynasty. Dynasty is a Python package that allows you to do Bayesian statistics like this. No typical MCS calculations, just define three functions and you are done in Dynasty. So roughly 10 to 12 kind of codes take care of it. So what Skilling introduced in nested sampling was that he said, let me introduce this parameter xi here, which is a function of lambda. And I'm defining xi as the amount of prior with likelihood value greater than this factor lambda. And if we construct this kind of a xi factor here, then our evidence integral will become this here. So eventually our evidence becomes the area under the L xi curve. The benefit is, instead of using two parameters here in the numerator, you are just left with one parameter. So you can calculate your posterior distribution along with xi in one go. So if you have this kind of a curve, how do you calculate area under it? The easiest way to do is to use the trapezoidal rule of integration. Like you construct blocks and then you just add the usual integration that you see. And to do it efficiently, what he said was, okay, my xi is from 0 to 1. What I will do is, I will sample n points on this axis randomly. Then I will say the point with largest value of xi is xi star. I will note the corresponding L xi star value. This is your L xi here, and your xi star is your xi here. Then I will label this worst point, like the point which is 1 less than your xi star, as your new xi. And then again I will note my values L xi over there. I will iterate. So eventually we are moving inside xi as we go on successive iterations. And once you have all of your values of xi and x, you can just do this kind of a staircase integration to get your value of fx. And since you've already noted your value of L over here, you can get your postulate distribution. Dynasty inputs value of xi at every step. So on final step, you will have your final evidence integral, which can give you basic by just doing a simple a minus b calculation. So we have a method of calculating our evidence integral. Now the question is to construct a likelihood function for our data set. So what I said was, all of you know Poisson distribution, right? Okay, so Poisson distribution is like a Gaussian distribution, but for a discrete set of values. So Gaussian function is like a limiting case for Poisson distribution. So what we said was that, let us assume that our sky has a perfect dipolar signal, and in each patch of the sky, we are sampling using a Poisson distribution by considering that we have a true signal and there are some fluctuations around it. So what this thing is going to do is that if we have a true signal, lambda here, then the probability of observing any sources in that part of the sky is given by this probability distribution here. Now for each patch of sky, we have a probability distribution like this. So our net likelihood would be a multiplication of all these probability distributions in different parts of the sky. For computational means, we define log likelihood. So in log space, instead of multiplication, we will have a summation. And due to selection effects, we have to switch our model from lambda to lambda times the value of selection function in that particular patch of the sky. How do we create different patches in the sky? Well, we use dynasty. Well, we use heat peaks. And using heat peaks, we divided our sky into roughly 50,000 grids. Heat peaks is really good if you want to do calculations on a scale. Like you can use it for any type of calculations, such as quantum mechanics, or if you really want to plot a spherical harmonics, do other stuff with your cartographic predictions. Heat peaks is your go-to thing if you are using that. After constructing this likelihood function, now we need to know what our model is. So we define a whole set of models. In statistical modeling, usually we need a null hypothesis with respect to which we are comparing all of our hypotheses. So our null hypothesis was that there is no dipole in the sky. So your sky would be unmodulated. The priors on this are given here. D is your dipole amplitude, L and B are your galactic coordinates. So L is like your galactic longitude, and B is like your galactic latitude. And N is the number density for your catalog. 0 to 30 was for the fine version of the Quasar catalog, while 0 to 50 number density was for the deeper version of the catalog. Then we said our main hypothesis is that we observe a dipolar modulation in the sky. Now, what is better than one dipole? You can have two dipoles in the sky. Actually, that was not the motivation for using double dipoles, but it's a higher order thing, so just take it like this. Then we say that, okay, we have a double dipole. Here, you will have two different angles here. So you will have cos theta 1 here, and you will have cos theta 2 here. So this model actually has 7 free parameters, including the frequency. Then we said, okay, we can also consider a double dipole, in which case your amplitudes and your cos thetas would be same, but your dipoles will point in opposite direction. In this case, we had priors like this. Then we constructed, function.
What does that call for specific priors?
So specific prior means unless otherwise stated, these are your priors. But if each hypothesis demands some additional priors, then you have those.
Okay, these are prior conditions.
Yeah, so these are the prior assumptions for your data. So you say that our data will be this, like our parameters are between this and this value. So unless otherwise mentioned, all parameters are these values. But if there is any specific value, any special value that we are using, that is distributed. Then we constructed 3 additional hypotheses In the first one, we assume that we have a dipolar modulation in the sky, but that points towards your CMB. In next one, we said, okay, we have a dipolar modulation in the sky, but it can be in any direction, but it should have a CMB velocity. And finally, we said that we have a CMB like dipole in the sky. The major problem here is calculating this D naught parameter. Why is there a problem? Because you can always say, hey Vasu, you have this formula here. Why not plug the values and you can just get to that plug it and be done. Well, the major problem is this assumption here. It turns out that this assumption is not true. This power law assumption for your sources is not true for most of your cosmological sources. So if your dn by d omega was indeed a power law function for your flux, then on a log plot, you should have seen a straight line. But here you are seeing a slight curve. Because of this, we use this modified approach here. Don't go into the specific, don't think too much about it. The main crux is using this approach here, we were able to calculate the distribution for a dipole amplitude and we took its mean value. So for our final version of the catalogue, we found that the dipole would have an amplitude of 0.008 if we were indeed assuming a velocity of 370 kilometers per second. Whereas for our deeper version of the catalogue, the dipole would be less in amplitude and will have this value. These were used as specific priors. After doing this, we fed everything to Python and we got our results. So for our shallow versions of the catalogue, here is our table of Bayes factors. Now you can ask what this galactic mass angle is. So here is the thing. You see around galactic plane we have backlit. So what we did was to ignore data around galactic planes by removing either 10 or 10 degrees above and below the galactic plane, 20 degrees above and below the galactic plane. But our idea here was to make sure that using this we are removing all the bad data points. But then exactly how much we should remove, because there is no standard prescription for it. So what we did was that we first tried by not removing any data point, then we removed some data points which were within 10 degrees of the galactic plane. Then we removed other data points which were within 20 degrees of the galactic plane. Similarly for 30 degrees and 40 degrees. And we calculated our Bayes vectors for all of them. So it turns out if you do this kind of analysis, I will talk about this 30 star a little bit later. What you find is that if you are removing sources up to 30 degree and are retaining sources above greater than 30 degree in your catalogue, then double dipole is dominating. For your 40 degree mass, your CMB, your matter dipole, is same as the CMB dipole. Okay, how do you make sense of this thing? Well, it turns out that if you look at the smooth version of the catalogue, there is an over density of sources present here, and there is an under density of sources present here. It means that your data set is bad in this region. That is why your double dipole is dominating, because you see, you can have the tip of one dipole here pointing in this direction, tip of another dipole pointing here in this direction, which can give you this kind of a structure. So, up to 30 degrees, we were seeing this kind of an effect here. And so we said, okay, in this range, our data is contaminated and is plagued by clustering, which is due to this overdensity and these underdensity region here. So after calculating for 40 degree galactic mass, we constructed another 30 star mask. In 30 star mask, we removed data within 30 degree of galactic plane, and we removed this circular patch present here. So our idea was that if we are implementing this kind of a dashed mask here, then all of the contaminated data points should be removed. And indeed, this is what happened. So with the 30 star mask, we again saw that kinematic dipole was same as the matter dipole, or your velocity inferred from matter dipole was same as the CMB velocity. And this means that there is no 5.7 sigma tension as was seen here. The cosmological principle holds and dark energy is indeed present here.
I was just asking, let's say, this is like kinematic dipoles and other dipoles. What constant factor are you seeing as a background? What can you say? How you are comparing that this can be correct? How you are taking out the prior this reference here? How you are taking the assumptions?
Assumptions for
While just say if it is a quadrupole, then you are taking some. These are some prior.
priors. So how are we constructing the
Yeah.
priors?
What is the constant that you are taking at that?
We are not using any. We are not using any constant. So you see, your dipole amplitude is between 0 and 1. This is delta. Your dipole amplitude cannot exceed 1. Your L and B, which are over 4 square. So we are essentially saying, okay, there can be a dipole in any direction of any amplitude. So essentially, these are not specific priors. Although our analysis is independent of the priors, this is not. But we have not used any special assumption while doing this kind of analysis. We said, okay, let's consider a completely generalized version. Now, this is for the shallower version, and you can see here, as we increase our galactic mass and our contaminated data points are increasing, our dipole direction and our dipole amplitude switches to the CMB direction and CMB value. So indeed, there is no 5.7 sigma tension present. What about the deeper data set? Well, here are the results. Ideally, if matter dipole was same as the kinematic dipole, then you should see an agreement here. But you don't see an agreement here. So what can be the problem? And furthermore, your dipole is pointing this side and your dipole is not matching with the kinematic agreement. How do you make sense of it? So Quasar authors had suspected that the deeper version might be contaminated. They had not proved it. So we said, okay, data set might be contaminated. And how do you prove it? So we said, since the shallow version was constructed by taking a slice from the deeper version, we will say that the dipole in the deeper version was actually the sum of dipole in the shallow version plus some extra contamination. And when we ran our analysis, we found out that contamination was present in this patch of the sky, which, as you can see in Quasar, is this region here. So what this means is that while constructing the selection function, these people had overestimated the amount of dust present around the galactic plane. So when this thing was sorted out, what we finally found out was that the catalogue is suffering from some contamination. However, after removing that contamination, matter dipole is same as the parametric dipole, and the tension is just because we are using bad statistics. The trouble in previous studies lie in how you are selecting your quasars. Yes. This work was significant because it was published as well as promoted by monthly notices of Royal Astronomical Society. So this work also featured on their website. Here are some references linked to my paper for those of you who want to read it. This club will be taking it. And the thing is, the story is not over yet. You know why? We have sorted this out in quasars, but unfortunately, this problem also persists in radio galaxies. But let me assure you, I am very near to showing that in radio galaxies, this problem is also because of using bad statistics. And I think that work will be published as a second paper for my master's thesis. So that is all from my end. The floor is open to questions.
The bad statistics, I think the bad statistical methods or that just use those things?
Both bad statistical methods as well as bad approach to how you select your data.
Okay, it's about data cleaning.
Yeah, both data cleaning and statistics. Both of them were flawed in previous.
Okay.
So, cosmological principle is still
It holds.
But there are other problems like bigger structures are being discovered by astronomers. Like, what's it called?
Yeah, but then cosmological principle holds on a scale that is much larger than those structures. Indeed, there are some structures, but on the scale on which cosmological principle is valid, on those scales, those superstructures are like this much in this big patch.
But the scale at which cosmological principle is valid is moderate.
No, cosmological principle is a fundamental assumption based on that your lambda scale model is constructed. So that is why this work was significant. Because if cosmological principle is wrong, then your standard model of cosmology breaks down. And it means all your perturbation equations, how structures evolved in the universe, how we are looking at CMB, everything changes.
So what does this work mean for lambda zero model?
It's and this is significant because after I published this, within 1 week, I received mail from around 20 esteemed researchers. Some of them were particle physicists, some of them were cosmologists, yet others were statisticians. And they were either in support of my work, they were like, yeah, you did a good work. But some other people who were staunch critics of the lambda CDM model, they were like, this work doesn't hold any significance. In fact, 2 of my former supervisors with whom I was working on proving that the dipole tension exists. Earlier I was in the second camp. Like if you had met me 1 year ago, I used to say that okay, this problem is there and lambda CDM model is gone, that kind of thing. I think MS22 keeps here. But when I started working this year, I found this thing. That is why in my second slide I'm questioning my own existence. Because what I used to believe for 1.5 years, all of that belief was gone in just one calculation. So, yeah, any other questions?
About power law, could you go back to the slide and the assumptions,
Yeah, the questions.
could you elaborate a little bit more?
So this one is a fundamental axiom. This holds regardless of your source in cosmology.
Also, like Alice in Baldwin explored this before the survey was done quite elaborately.
Yes.
In the 1980s.
Yeah, so Alice Baldwin gave this formula. They said that if there is an anisotropy, then you should see like this. First test of this formula was done in 2002 by 2 people, Blake and Moore. And since then, like it was actually done in radio catalog. That is why radio problem is much more significant. Quasar one is a recent thing that started in 2020s. So we have shown that it's not the case. For radios, the problem has been there for almost 2 decades, like more than 2 decades. And I hope that we will be able to show the system. So it is system. Any other doubts?
भैया क्वेज़ार की रेडियो सिग्नल्स यूज होते हैं
Quasars are not all frequencies. It's how you observe them.
रेडियो का हमें ब्लैक होल की रेडियो सिग्नल नहीं होता
Yeah. See, you can observe. In fact, what I just say is, here, while studying quasars, these guys use infrared data. Whereas in our study, we have used optical data.
and I didn't understand what the 4.9 sigma significance like what is the distribution में कहाँ पे कौन सा result होती है
Far away, almost 100.
but what was the result like dipole
The dipole is the discrepancy between your CMB dipole and your meta dipole was 4.9 sigma.
like it was higher or
It was higher. And it had like 28 degree offset. So if your CMB dipole is this red spot, what these people found was that it was in the blue spot and it had twice the strength. What these people found out was that if your CMB dipole is here, their dipole would be here with almost 3 times that.
but still there is a dipole in CMB it's still non-isotropic
It has a dipole, but as of now, it is due to our motion towards this hotspot in the sky. It's not an inherent dipole. Yeah, there is an inherent dipole when you break your CMB into using spherical objects at this level. But this thing here that we are studying, this is due to a motion. So it's not a true dipole, it's just an observational thing.
ये डाइपोल का मीनिंग क्या है यहाँ?
Sorry?
डाइपोल का मीनिंग यहाँ से
ये डाइपोलर मॉड्यूलेशन है आपके डेटा का। बेसिकली इसका मतलब है कि एक साइड में आपका टेम्परेचर is higher than what you are observing in the other side of the sky.
It's a dipole of temperature.
Yeah, it's a dipole near temperature. So if you have you will do this in your second semester, I hope so. Like you will. So what you will see is that if you are moving with relativistic speeds, then your distribution would be coned up like this in your direction of motion. This is actually an effect of Doppler boosting, and I think you are in MS23, right? You will learn about this in later parts of your electrodynamics course, especially if you learn special relativity and its implications for electrodynamics. Otherwise, you can always go to Purcell's book and read it. So just open Berkeley Physics Volume 2, try to read second or third last chapter. You will see what dynamics. Yeah, any other questions? Also, one final thing. If you guys want to learn about this one, do let me know. I'm also ready.
there is then homogeneous but not isotropic. What's the difference between homogeneous and isotropic?
Homogeneity means your density is same in all patches of the sky. Isotropy means in whichever direction you go, the universe should be the same.
Using that same thing.
Homogeneity implies isotropy, but it's not opposite. It's a one-way relation.
Okay, if there is isotropic, that doesn't really implies that the homogeneous he over.
Yeah?
Like you said that it's a one-way relation.
Sorry. Isotropy implies homogeneity. My bad. Sorry. Thanks for pointing. Isotropy implies homogeneity, but it's not.
So how can something can be homogeneous but not isotropic?
You can have number density, equal number density in different. You can have equal number density in different parts of the universe. But then your space is expanding in a dipolar fashion. Instead of expanding like a balloon, it's expanding like a balloon. So picture this. Let's say you have a space. Let's say you have a balloon. And your balloon is how your universe will expand. And on the surface of the balloon, you have equal distribution of things. However, the balloon is expanding, it will have the same number density. But if an egg is expanding, then even though it will have the same number density, it will have a different expansion style.
In the definition of homogeneity, constant density is used. It is the density of discrete density.
Matter density, like density of your components. Density of your universe constituents. Matter, radiation, and energy.
Okay, and density.
Yeah, the whole energy level.
Okay.
Broadly, at your level, you should understand it like this.
So I think
Okay, one factor.
टेम्परेचर के डिफरेंस मतलब ये टेम्परेचर का डिफरेंस हम आप बोल रहे हैं अभी मतलब एनिस्ट्रोपी आइसोट्रोपी नहीं है ये
No, I'm
जो
saying-
पहले वाला ये में था
No,
स्लाइड
no, I'm not saying. What I'm trying to say is that this dipolar modulation of the temperature is due to our motion towards this part of the sky with a specific velocity. It's not an inherent modulation. It's not an inherent feature of it. It is just because you are moving towards a particular patch in the sky.
मतलब कि अगर किसी के से मूव करने की वजह से टेम्परेचर वेरी करता है मोशन के ये से मोशन
आपके रूम सपोज दैट आप सीधी ऑब्जर्व करें अगर आप स्टेशनरी हो यूनिवर्स में तो आपको हर डायरेक्शन में टेम्परेचर सेम मिलेगा और अगर आप सपोज दैट इस डायरेक्शन में मूव कर रहे हैं सो स्पेशल रिलेटिविटी बिकॉज ऑफ दिस फॉर्मूला दैट आई शोड कि आपके सामने जो है तो आपको ज्यादा टेम्परेचर दिखाई देगा आपके पीछे आपको टेम्परेचर दिखाई देगा
क्यों
इट्स अ स्पेशल रिलेटिविस्टिक इफेक्ट It's an effect. Like there is no why. Why is because we are moving. motion में से ये effect generate होगा?
It is related to the Andra effect in a way. I don't think so. Okay, right. Yeah. You have a question. Okay, so this is a bit of
Sir, so when you said that we move towards a particular point, is it just as a result of like redshift, like of the Lorentz redshift, or is it that there is something about that point?
There is something which is attracting us towards that spot.
So is that point special, and if so, because of what reason?
So can you please restate the question?
Is that point special in some way? Because like we move towards it.
No, that point is not special. The only thing is, at redshift of roughly 0.01, there is a large structure present over there. At redshift of 0.01, which is roughly 3000 kilometers per second, at redshift in scale factor only. This part has a superstructure, which is exerting a gravitational attraction to our solar system, which is causing us to move towards that spot.
And what is that superstructure? A collection of galaxies?
I think it is called Laniakea. Something. Yeah, Laniakea's supercluster. But then there are the other people who will say it is not Laniakea, it is some dark matter distribution. So that one is still under question, but as of now, I would say you should think about it as Laniakea. So I think I will take other questions outside the class.
So that's it. Thank you, Bhaiya. Thank you everyone for coming over. This is the first of our MS thesis talk. We would soon come up with more of MS thesis talk. So you would get to know like how the actual research looks like. Sometimes it would be intimidating for you for the first time, but yeah, just
It was much more intimidating for me even in my third year. Believe me, it took me around 2-3 months to even understand the research problems, so it is okay if you don't understand it.
So yeah.